Thanks very much. I will make my introductory comments extremely brief because the last talk just perfectly teed up. What an amazing coincidence! The panel here that's about to follow, and I will just maybe I'll introduce everybody, and then so they can just rotate through, and then if you could hold your questions for the end, we should have a lively question and answer session following that. So we have four wonderful people looking at sort of burrowing down to various parts of the battery storage questions, starting with Jeremy Cowperthwaite, who is at Maxwell Technologies, David Eaglesham, who's at Pellion Technologies, June Liu at Pacific Northwest National Laboratory, and Galen Stucky here, the local guy from UC Santa Barbara. So we are going to sort of do a quick survey of this terrain. They're going to set it up for us, and then we can plunge in and drill down to some of the specific questions following that wonderful overview we had. So, Jeremy, you want to start it off? I'm sorry? Oh, I'm sorry. I was looking at the order of the program. Maybe I'm looking at the wrong page of the program. Okay, well, David can go first, and I can also. Oh, okay. Okay, great.
Either way is fine with me. Okay. Oh. I'm not going to be able to do this one. I don't think. Yeah.
Okay, so if you were paying attention, I am Dave Eaglesham. So I'm Dave Eaglesham. I'm with Pellion Technologies. Pellion is a company that was formed a little over 3 years ago to pursue just one of the thrusts that George was talking about. So the company was formed around the notion that if you can just do something that looks basically like a lithium-ion battery, but do it with magnesium, you will double the charge. That gets you about double the energy density. It also gets you a vastly more abundant material set, so you can drive cost more effectively. So I could stand here and talk about what Pellion's doing, but what the organizers asked me to do is to provide a broad survey of what are the cost challenges with the storage business at the big picture energy level. And I'll try to do that in 5 minutes. I'm not sure that's realistic, but we'll try. Okay, so I want to begin. I usually begin talking about batteries with this caveat. So this is a quote regarding battery companies being a mechanism for swindling the public by stock companies. This quote does not come from a disgruntled A123 stockholder or from an even less gruntled Republican committee. This comes from this guy back in the 1880s. So with that as a background, I want to talk about some of these storage market projections. So this is a hot topic right now. So there's a lot of discussion around the growth of the grid market, and the projections here are phenomenal, and they're pretty near term, right? So people are talking about a sort of 5-year horizon to $100 billion markets. And most of them, there's a whole bunch of stuff. The first 3 things that you see there are triggered. They're all analyst reports, and they're basically leveraging this Electric Power Research Institute thing at the bottom, which is it's a great report. It's well structured. They sit down and they walk through what the demand looks like. The figure at the bottom is that this is the slide that launched 1,000 startups. So what it implies, let me just maybe walk through what the figure means. So here's the cost per kilowatt hour, and to the discussion that we just had, this is battery kilowatt hour, not electricity kilowatt hour. So this says that at $650 per kilowatt hour of capital cost on the battery, which is not that far below current lithium ion, there's a phenomenal amount of demand. So this is, the VC guys get all excited about this stuff. So this says if you can just be 30% better than existing lithium ion technology, you can open up a colossal demand. Okay, so the issue with this is that the way the Electric Power Research Institute constructed their pricing, it was basically based around 2010 market, and then they extrapolated demand from there. So then so they took two things. They took time of day differences, which are largely set by the fact that there is no storage on the grid today. So that's the time of day difference, and then they extrapolate the market based on renewable penetration and a whole bunch of other things. So this is maybe my single message here. So I want to peg a few kind of price numbers in people's head. First, I want to do a quick translation of the discussion again that we just had. So 650 bucks per kilowatt hour of capital cost translates into something like 18 cents a kilowatt hour if you treat it as an equivalent generation asset and all the rest of the stuff, right? So 650 bucks a watt of capex. It obviously depends on how often you're using the battery. It depends on how long the battery survives, but it's roughly in there, right? So 18 cents a kilowatt hour, that's a generation cost. Now, if you compare your generation cost then with what is it actually cost to generate and the energy that we pull from the grid, so base load is about 3 cents a kilowatt hour, and in fact, that cost, when the EPRI guys built the cost model, they actually assumed that you're buying electricity at about 3 cents a kilowatt hour. Combined cycle gas runs somewhere around 6, depending on how you run it, depending on how big the plant is, a whole bunch of other stuff. Compressed air energy storage, which is the only large-scale storage option other than hydro that people use today, is somewhere around 6 cents also. Right? So I want people to sort of think about these numbers. So 18 cents a kilowatt hour, and this is roughly going to translate into maybe my single bullet, which is that the market is real, the demand is there, but the price points are going to be about a factor 3 lower than what people are projecting from these existing studies. Okay, so cheap gas, smart grid. I didn't really talk about smart grid. The smart grid obviously has the effect of increasing the flexibility on the grid, and that drives down the need for some of these expensive band-aid solutions where you try to band-aid storage in. If you have a smart grid, you maybe don't need to do that, and that's going to drive the cost points much lower. Okay. One other study, which maybe goes to the other extreme, that I want to maybe draw to people's attention. So the Enel guys did a study of renewable energy futures. This is a cost-optimized model with a goal of meeting 100% of electricity demand 24/7 in the US with 90% renewable penetration. So this is maybe a somewhat academic exercise, but I think it's a very useful exercise in terms of pegging our minds to the way that you can potentially solve these problems. So the way they solve these things, so they look at the intermittency on these various, or the variability in solar and wind and all these other things, and they basically design a system so that things are geographically distributed, and as one goes down, the other one's coming up, and you basically generate a grid which has it has pretty much renewables coming on, so wind is coming on, the sun's coming off, and so on. Okay, in this model, they actually only jacked in something like 10% of total electricity demand is storage. And all that 10%, by the way, was all compressed air. The way they fixed the fluctuation problem is with transmission capacity. So to fix the transmission problem, it's easier to transmit from a sunny area to a not sunny area than it is to store the electricity and pay it back later on. Okay, so I want people to have this number in mind. Again, so 10%, if 10% of all electricity used in the United States was put through a battery, that's still a very, very huge market for the battery market, but it's nowhere near as big as some of the other projections. Okay, so what are the opportunities? So where are the real opportunities? You know, I think when we look at it, high energy density, it's maybe not very visionary, but there is an existing market. The existing market is very strongly driven by energy density. It runs about $15 billion a year, and there is almost no system overhead, right? So you can minimize the system overhead with that thing. If you want to go after the grid storage market, I think, again, this is very much in line with what George is talking about. You really have to go after cell chemistries that have radically low materials costs. The picture on the right shows sort of cost of goods sold. It's a it's actually built out of company returns. So you'll see R&D costs and SG&A and all that kind of stuff in there. The vast majority of the cost of goods sold of a battery is materials. So unlike photovoltaics, in which the cost of the materials, the semiconductor materials, is a very small piece of the cost of the module, in a battery, the vast majority of the cost of the battery is actually materials cost. So innovating materials around low-cost materials is a critical piece of trying to drive these overall cost goals. Transportation, I think we all accept that. Safer chemistries, I think, again, George touched on this, but I believe that in terms of both of rate of adoption and of the qualification time for a technology, I think it's really terrific to be able to get away from the exothermic releases that are associated either with lithium-ion or with liquid sodium. And that narrows your opportunity space quite a lot, but I think that gets into a place where you'll have rapid adoption. Last comment is high energy efficiency. So thermal management costs are a big piece of the system problem on these big batteries. So if you look at the total system integration costs of a large battery, a lot of that is actually thermal management, and raising the energy efficiency of the battery is a way to get around that. Okay, so that's all I have. Thank you.
Okay, I'm Jeremy Cowperthwaite, and I'm from Maxwell Technologies, so a little bit of a different angle from probably the rest of the speakers here. I'm actually a UCSB alum, so happy to be back in the area. And I'll say before I start that I'm responsible at Maxwell now for running a business that's focused on engine starting, which is a good application for these ultracapacitors. Let's see if I can get this. Oh. I thought I'd start by talking about the basic application. This is fairly fundamental type of information. Oh, stay near the mic. I forgot I'm not mic'd up, sorry. The basic application, you have a primary energy source, of course, and these are typically, there's a need to over-design these to be able to supply the power as well as the energy needs of the application. On the application side, you have continuous power usage, of course, peak power demand, and then there's some power in excess that can be returned back to the energy source in a limited way through energy capture. When we bring in the ultracapacitor, things change. First of all, we're able to downsize the primary energy source because the ultracapacitor is able to handle the peak energy requirements. The application side remains the same. And also, because of the fast time constant of the ultracapacitor, we're actually able to have much better charge acceptance than other energy sources. So we're able to capture more of the excess power coming back from the application. Oh, okay, getting the hang of this. And this is the basic usage model for ultracapacitors. We have two sort of fundamental features. The first is peak shaving. So basically, we come into play when there's a shortage of power available from the primary energy source. And the second is basically UPS application shown on the bottom of the chart, where we fill in the gaps from a UPS standpoint. I actually have one of our products with me here. This is the main building block of all of Maxwell's and really the industry's products. We are the leader in ultracapacitor, so it's hard to really talk about the ultracapacitor business without using our product to demonstrate it. This is a 3,000 farad cell. It's a 2.7 volt cell. I'm sure an audience like this knows sort of the fundamental principles of activated carbon. There's basically 30 to 50 football fields worth of area in a cell like this when you multiply it all out. And the differentiator with our cells versus the rest of the industries is that ours are made through what we call our dry electrode process. So this has a lot of IP built around it, and it's also very applicable to the battery industry, and we have a lot of interest from companies making various types of battery chemistries in our dry electrode process. A little bit about our applications. These are Maxwell's applications, as well as the worldwide ultracapacitor applications. Starting in the top left, transportation. This is one of our biggest areas. So we are present now in rail, bus, hybrid bus, auto, and then also construction. Just to give you an idea of the size of the business, there are currently greater than 10,000 hybrid buses in China with ultracapacitor regen energy storage in place. And that number is growing every day. And depending on how subsidies come out in China, it will continue to grow at a rapid rate. In auto, we're present in Europe. This is in France. PSA has about 1 million vehicles on the road now with start-stop systems that are enabled by capacitors. These are 2.7 volt cells that are configured in series with a 12 volt lead-acid battery, and they come into play during a start-stop event. Moving over to renewables, biggest presence here is in wind. There are ultracapacitors now in approximately 25 to 30,000 wind turbines around the world. And a lot of those are in China, but also there's a large presence in Europe too of wind turbines, and it's really just starting relatively here in the United States. Also solar and various energy harvesting applications. Moving down to industrial, cranes, valves, mining, smart grid. These are all areas where ultracapacitors have a good application due to the power performance. And then finally, on the electronics side, largely in consumer, but in some commercial electronics, there's greater than somewhere between 2 and 5 million solid-state disk drives now that are out in the field with Maxwell ultracapacitors enabling them. Other applications are non-volatile RAM and also UPS. Of course, UPS with the appropriate time duration, because we again are a power device, and so we do have limitations in energy. Final slide. Bottom right, you can see our portfolio of products. We have cells ranging from a farad all the way up to 3,000 farads, and then modules that range all the way from 16 volts to 125 volts. And these all get built into systems of varying complexity. Talking about the future, looking forward, there are 3 big enablers, 3 big areas that we're focused on in the ultracapacitor industry. First is increasing the energy density. So we have active programs in place to increase the energy density primarily through voltage increase, but also through capacitance increase and also packaging. And energy density increases will lead to further penetration, we believe, in transportation. There are transportation applications currently, and it's been this way for a number of years, that have been telling us that we really like the power performance of your device. If you could just increase the energy density a little bit, not to where batteries are, but a little bit, we would have much greater penetration. So that's one of our big foci. Power density. This again is voltage, and then of course there's a resistance term in the denominator. So ESR needs to come down also. Power density increases are going to really enable the consumer electronics market. Smartphones, tablets, all of the mobile devices that the world has adopted now are all really, really thirsty for longer battery life, and we feel that ultracapacitors, if we can peak shave the power requirements in those devices, will give you much better battery life. And then, of course, we have continuous cost reduction. So we have dramatically reduced the cost of these devices over the last 5 years as we've grown. We've come from about a $60, say, material cost for a part like this to well under $20. We need to probably come down by not another order of magnitude, but we need to come down significantly still to generate further penetration in what we feel is a very elastic market. And we, of course, have programs in place, and I'm sure our competitors do, as these ultracapacitor firms pop up all over the world, to come out with much more effective ultracapacitor power devices. Thank you.
Good morning. The topic is different from the program because sometimes my secretary decides what talk I should give. So I'm going to talk about some specific important issues we need to consider for both transportation and grid applications. So how this works? George and David give very good introduction to energy storage program. So I don't need to repeat many of the issues. There are two important areas. One is in the renewable and grid application, another is in the transportation. For transportation application in particular, we are really considering how do we increase the energy density of the batteries and many other issues. So I'm using this kind of chart to show you that now we're working on lithium-ion batteries that is probably good for some of the short-term applications. But if you want to really increase the energy density, you need to go far, involving many other chemistry. However, right now, even for transportation, in addition to the specific energy density, there are many, many other important issues we consider. One is safety. Really, I think the safety problem is the issue that can derail us by a number of years. So we need to take a very hard look at that. Now I'm using this chart to kind of show why safety is a big problem in batteries. So this on the, I don't know how to make this work, but on the left-hand side, we show the sort of the chemical potential of the electrolyte, and also the other side shows the chemical potential of the electrode material. Top is the anode and bottom is the cathode. As you can see, if you look at the so-called normal and the HOMO energy level of the typical electrolyte and compare that with the energy level of the electrode material, really, ideally, you want to be working within this stability window. Otherwise, you get into trouble. Now, if we use graphite, even graphite, in the future we want to use lithium, you are on the high side. That means intrinsically, you have charge transfer from the electrode material to the electrolyte. That really causes the so-called dendrite formation and the fire, those kind of things. You can have the same kind of issue in the cathode material. So you can do a lot of things, try to prevent this. You put a membrane there. If the membrane is not good enough, you put a ceramic on the membrane, try to separate the different components, those kind of things. But really, you are fighting against the thermodynamics. So what we really need to look at is, are there any intrinsic ways to solve this problem? So I'm going to give you two examples. One is, if we look at the anode material, that's where you form the dendrite. Thermodynamically, you always get this SEI formation, this dendrite, those kind of things. Are there any way you can change that situation so that if you form dendrite, it will disappear by itself. So this is a kind of a study that's currently supported by JCSA that we are looking into chemistry's additives in the solution to make the dendrite, those kind of things, to self-disappear, or this is what we call self-repairing surface. I think those kind of new concepts could lead to much safer batteries. Now, in addition to lithium chemistry, we can look at other chemistry that are intrinsically safer. So one example I'm giving here is the magnesium battery that is what Dave works on. Of course, we're thinking about magnesium battery that you have 2 electrons and can get you to high specific energy density and it's more abundant, all those things. However, another very important issue in this, again, this is partially supported by JCSA right now, is that magnesium, for whatever reason, is fundamentally different from lithium. That we have developed a few generations of electrolyte and electrode material for this chemistry. If you look at the surface, we don't do anything, and it doesn't form the dendrite on the magnesium. So you always end up with this very, very smooth surface. So those are the 2 examples I want to give to intrinsically make the battery much safer for transportation applications. Now I'm going to go to the grid scale renewable energy storage. Now in this case, it's very complicated. So I'm using this sort of chart to compare the energy storage for transportation, which is a very small box on the far side. And the battery doesn't need to be very big. And then we are mostly considering lithium-ion battery for that. We need to reduce the cost. But if you look at other applications, the energy scale or power scale goes very, very wide range. And there's not really a single technology that will solve all the problems. I also want to point out, Dave kind of alluded to that, the cost requirement for different applications are different. For example, these are the sort of requirement for you to store the energy during the day and move it to night, do those kind of things. There really, you need the technology to be very, very inexpensive. But for other applications, like power application, frequency regulation, balancing requirement, those kind of things, the cost can be higher. And that was shown in the chart David showed that from the April study that the cost requirement for frequency regulation can be much higher. So there's not a single technology that we will use to do all these things. And other dimension that I don't show here is that all these applications, the performance requirement is also different. For example, how fast you want to discharge the battery, how long you want to store the energy is also different. Here you need the charge time can be much longer. You need to store the energy for a longer period of time. But here, the frequency balancing requirement, the battery need to be discharged much faster. So for those things, some of the lithium-ion batteries you can stretch to the power application, but it's not likely for the so-called true energy storage sense. So if you go to the literature, there's a lot of discussion and debate or question on really where energy storage is needed, how much energy is needed, for what application, all those kind of things. More important, who is going to pay for all those kind of stuff? So this is a much more complicated story than just the transportation that I need a better box to put it into the car. And so this is some of the studies sponsored by DOE that we published very recently. Just try to do the analysis carefully on exactly what we need to do. So in this study, we take the Western state. We started in the Western state. We try to apply to the whole country later on. And then we're just considering one application, the balancing requirement, because the problem is too big. We cannot do everything right now. And in the Western state, if we assume 20 gigawatt, we should install the wind capacity in 2020. And this is an amount of storage capacity we roughly need for the Western state, but just for the balancing requirement. So the market is there. Whether we do it or not is different. That depends on cost and many other things. And we did some other pretty interesting analysis associated with this. For example, for balancing requirement, we can also analyze the capital cost of different technologies to see which technology can be suited for this kind of application. So for example, sodium-sulfur battery, supercapacitor, flywheels, and other technologies, even lithium-ion and redox flow batteries, might be applicable for in a number of years for the balancing requirement. But if we do the same analysis for storing energy during the day and dump it to the wind, do those kind of things. Now, all these technologies are really right now too expensive, so we need to think about new ideas and new concepts. So what are the, before I go off on that, there's another thing I want to point out is from the end user, you consider the energy storage from probably slightly different perspective. Even for off-grid application, you can do things different. And here I'm giving Secretary Cho give this example of PV module cost in China. It really dropped so drastically in the last few years. And if you look at this whole thing, so in this package, that actually includes a battery, which is a lead-acid battery. Lead-acid battery is still 60% of all the market today, but even in China, they have close to 90% of the manufacturing capacities. Now, currently, for typical home, the cost of installation cost of the PV is $25,000 or about $30,000 or so. In the future, it's going to go down below $10,000 or so. So if you want to include a battery in this whole package, your battery really need to be less. For example, I'm throwing out a random number. So the customer look at how much I'm going to pay today. You need to be less than $1,000 probably. So what technology can you potentially do that associated with storing energy day and night? One way to go is to go to abundant material. So this is some of the work sponsored by ARPA-E and the Office of Electricity we've been working on. So let's say instead of using lithium, let's go to sodium battery. So use sodium. So there are two approaches. The high temperature sodium battery that's supported by ARPA-E, but really that is still need to be risky and the cost is need to be higher. But if you can make a room temperature sodium battery, you're probably much better off. So that's another thing we have been working on. And now, George already mentioned the redox flow battery. Now, the reason you work on redox flow battery is you get rid of the electrode and many of the manufacturing issues, and the electrolyte can be very inexpensive. So the whole package can be very, very inexpensive. Of course, the limitation is that redox flow battery, the solubility of the active species is very limited. So that inherently increases the volume, the whole total cost, those kind of things. So what kind of things you can do to increase not only the efficiency, but also the energy density of the redox flow battery is a challenge. We have been working on that for a few years, and this technology that get a big investment, a new company in Seattle just to do that. So with that, I will stop. Thank you very much.
So good morning. I'm Galen Stucky, and I'm the local boy. I like to hear that word at this stage of my life. I'm going to talk a little bit about chemists. I'm a materials chemist, and it's appropriate, I think, that I do that. See, I guess I have to figure out how to make this switch. Which button do I push? Right button. There we go. I got it. So the question is, we've been hearing a lot of storing energy, and one of the most efficient ways to do that is with chemicals, and as evidenced from the slide that you see here, whether you look at it from the volumetric or the gravimetric point of view. And you don't get something for nothing, I've learned over many years. In fact, and so you get energy, you have a lot of energy density, energy storage, but it costs you to make that. And the question is, what can we do in terms of using renewable energy sources to complete the cycle, that is, actually be able to do something about, use a very abundant reactants we have to work with. We think of carbon dioxide and nitrogen, for example, as our reactants. And it goes back to, there's two ways to look at this, and this is the one that comes back from natural gas flaring, where we burn 130 billion cubic meters of gas per year as of 2010. And the one good news that's coming out is that that number is going down. And so the application, the idea of using chemistry, for example, to reduce the CO2 concentrations by using renewable energy sources to do that is a noble idea. It's very much in the infancy, but there's some major things that need to be considered as regarding other things that can be done in parallel to that, and this is one of them. It turns out, if this is looking at this, what's been done, there's about a 20% decrease as of 2010. So there's about a 13 billion cubic meter decline, and which is 30 million tons of less CO2 that's emitted, and 6 million cars off the road. And you can look at it at where we are, which is about 133 billion cubic meters that we still have to do something about, and that's 30% of the European community consumption per year. So we've still got a lot on mind. But looking at it from the other side, that is looking at how we can do something with electrocatalytic and photocatalytic production of chemicals, or conversion of chemicals in an easy way so we can store electrical energy and produce the hydrocarbon fuels and chemicals from CO2, water, and renewable energy sources. And so there's intense effort going on, and this is, I'm sure all of you know, through the Joint Center for Artificial Photosynthesis, which involves quite a number, both Caltech and also Berkeley, but also San Diego, Stanford, and UCSB are involved in this as well. And I'll say a few words about this, but this is what I just described previously is the bottom line here is the goal, a cost-efficient method to produce fuels using only sunlight, water, carbon dioxide. And I'll say a few more words about that in this talk. A couple of questions come up as a chemist. What can you do? Can you make something out of carbon dioxide besides carbon monoxide and other simple things? And the answer to that is yes. And this is some very nice work from Tom Jaramillo, who is a UCSB postdoctoral graduate student, actually, worked with Eric McFarland and also partly with me, is now on the faculty at Stanford. And he's shown just recently that you can take CO2 and using electrocatalysis, convert it into 16 different products. This is, as far as I know, the world's record for what's available, including the simple monocarbon species such as carbon monoxide, methane, for example, some of the and dicarbon, ethylene, and so on, as well as some of the tricarbon systems as well. And he did it with a relatively simple electrolysis configuration, which is shown here, and using GC as the analysis on it. And the issues here, and this comes from Whipple and his co-workers at the University of Illinois-Urbana, who did a kind of data mining literature search summarizing the energy efficiency. The alkaline electrolyzers are for water splitting, and the energy efficiency for that, which is suitable, it's appropriate, about 70%. There was moderate energy efficiency for the CO2 conversion, and it's easy to make carbon monoxide and formaldehyde, but it gets to be a problem when you're making the hydrocarbons, and primarily because of overpotential problems with that. And this is another one of the, just to illustrate from a chemistry, materials, catalyst point of view, summary again from Whipple, where the problems are. And basically we need to do something about increasing the energy efficiency. That's a major fundamental goal, of course, for the overall process, and also increase the reaction rate. And both of these, in the end, depend upon having the right catalyst and finding that. So I wanted to say a few words about that. A couple of approaches, one approach that we're coming to, you know, I was at DuPont for 4 years, and in a catalyst group there working, and one of the, we went to this was many years ago, went to the early stages of doing high throughput experimentation, and the old chemists there laughed at it because they said, this is because you don't know anything. Well, the fact is that's still true. There's a lot of things we don't know about how really to design appropriately a figure of merit performing catalyst or material, and particularly in the systems configuration. So one approach which is being, which we came out from Jifan and my group, and also has been developed by, and it's currently being used at JCAP, and I'll say, tie that in collaboration with JCAP, is basically using inkjet printing, and where you can get up to 8 different compositions, for example, which are shown here, and you can print them out very quickly using, as shown here, to make screening. You can do photoelectrochemical screening, and this was a 3-electrode system, a really scanning probe device, which was developed at Caltech and JCAP, and using a drop of electrolyte. Each one of these little dots that you make, they can be nanostructured dots, actually, and as far as the oxide is concerned. They can be porous, mesostructured, if you wish. And you can do, you can get they're about 1 millimeter in diameter. You can get very fast, about 5,000. You can get up to over 500,000 of these individual dots printed in about an hour. And typically in real life, it's more like 50,000 that you do. So you have that many that you can characterize and make your library. In this case, it's a 4-component library containing iron, nickel, titanium, and cobalt oxides. And there, in this plate, there's about 1,800 dots, and there were 3 plots, 3 that were 3 plates that were made in this example. This is somewhat old. This was presented at an Electrochemical Society conference, which is indicated here in 2012, and things have progressed significantly since then. But the point is that you can then look for systems and look for over-potential problems, and this shows the printing of that and mapping out the figure of merit for some OER catalysts, and you can look at it on the left side, it's a function of the position on the plate, and the right side, it's looking at it in context of the phase diagram for the 4 components, and then you can take slices, of course, to it as well. The blue is not good, that has the high over potential. The red, if you can find them, they're scarce. The yellow, green is better, and yellow is better, and the red is the best, but they're, as you can see, they're few and far between, but they still exist there. And there's variables in here, quite many variables in here, which have to do with annealing. And these are deposited, of course, on a conductive glass slide or plate. So just finally, I want to say a little bit about creating an autonomous unit to do artificial photosynthesis. And this is from particularly Martin Moskovitz and Eric McFarland here at UCSB. Really are the drivers behind this project, and have done some, I think, quite remarkable work in bringing this to at least the prototypes and the models to fruition. And the whole idea, of course, you're going to combine a photovoltaic along with a catalyst. You need an oxidation catalyst, you need a reduction product catalyst as well, as indicated on this slide. This was just came out in nanoletters. It's I guess ASAP, or anyway, it's available if you would care to look at this. And this is an example of an application. We took HBR for a couple of reasons. Number one is, one part is the stability of this. That is, we wanted to make sure that we could create a system involving the semiconductors, or what we needed, the PN junction system, whatever we wanted to use for that, and package it in a way that would have a long lifetime. And it does have a very good lifetime. We haven't done it for extensive lifetimes, but certainly 24 hours, that period is very sustainable. And it gives about a 7% efficiency for conversion of HBr or HI solution. So it's a rather corrosive electrolyte. There's good reason, we have reasons for doing that besides the corrosive issue. You can also oxidize natural gas with bromine, and you then use that to convert it into fuels and to chemicals as well. So I think that's my last slide, and I think that's what I have to say. Thank you.
I'm going to start by asking a number of really general questions, just to sort of broaden out the conversation a little bit, and then in a few minutes we will open up the microphones because I'm sure people have more sophisticated, more technical questions than I do. But I do want to sort of put this in the context, in a broader context. I want to turn first to David and ask, when you talk to the solar guys, you used to be a solar guy, they say, storage, you don't have to worry about storage for a long time. It's not a showstopper for us, nothing to see here, move along, move along. And when you talk on the other side to people who are, talking about renewables on the grid, they say, it's impossible because there's no storage. So I guess, without storage, it's basically a dead issue. So first of all, sort of help me ground truth out. At what point does it become really a showstopper for renewables on the grid?
So it depends which renewable, right? I guess the way I think of it as a solar guy, so disclaimer there. So there's sort of a 20-some% difference between day and night usage. So if you start from today's grid, you can bleed in something like 20% solar before you need to worry about storage. If you look at the way the NWEL study is sort of designed conceptually, they basically start with that 20% solar, and then for every megawatt of solar that you add beyond that, you jack in about a megawatt or so of wind to get the night generation, right? And so if you design the system that way, then the need for storage is pretty minimal as you grow it, and again that's the thinking behind the NWEL study. Because the other issue is grid robustness, right? So the grid has to be robust in addition, and I think that's adding, from the utility perspective, that adds some additional need for storage, depending particularly on how the storage is implemented. Right?
So
I think maybe one final comment. So if you look at the penetration in Europe, where the penetration is really high, they have run into problems in Europe. It's become an issue. But in the case of Europe, the generation is dominated by wind, and it's dominated by wind in the North Sea, and there are actually very weak links between the generating assets in the north and the consumption centers, which are much further south. Right? So that's an example where you can run into trouble, but it's largely a problem of design, in my opinion.
yeah, because you keep hearing how much renewable Europe has, and they don't seem to be wringing their hands a lot about batteries. But I guess it's a different story, clearly. So, June, June.
So, is this on?
Yeah.
So I think your question is not completely accurate, because I have interaction with a few major solar companies. They do want to consider the batteries for the solar PV they are selling, but the problem is they don't have good option right now. They just stick with the lead acid battery, and one of the companies, they actually, when they started, they set up another company to develop a different battery for the system, but then eventually the cost is too high for them to really get in the business, so they just went back to lead acid batteries. So if you can really develop a technology that's sort of comparable to lead acid battery, that would be very useful.
Yeah. So how much would that reduce the need for grid-wide storage? If I can put this in my house, that was a very intriguing slide you showed. If I can just put this in my house and say, well, then maybe the grid, does the grid at some point just become irrelevant, or grid storage?
Not really, because depending on where the market is, how you are going to use it. If you go to China, right, you can do the calculation, the setting efficiency of your solar panel, the high-rise buildings. You cannot, there's not sufficient space for you to have individual solar panels for each apartment. Then you have to go to the sort of solar farm, those kind of things. So the marketplace is slightly more complicated than in our mind as scientists. So really, you have to consider how it's going to be implicated.
Yeah, and let me ask you, Jeremy, since this is the first time I've seen an ultracapacitor, and I've heard of capacitors as little parts on chips, on boards and so on, but I always thought there was just a tiny flash of power, and that was it. This must, could you give us a feel for how, over what period of time this could discharge and provide power, for example?
Well, so I guess first of all, just to put it in perspective, I think when we were in our in college and learning from textbooks, and actually even today, the students that I hire out of UC San Diego at Maxwell, they think of capacitance in terms of micro, pico, nano types of farads. So this is obviously 3,000 farads. So it's a much larger amount of energy. But the discharge, we typically say that we have about a half to a 1 second time constant, just to give you a feel for it, and we typically go into applications that run for anywhere from 0 to 30 seconds, kind of time frame, which is part of the reason why we need to increase the energy density in these things, so we can actually extend that further for like transportation applications where they want to sail in mild hybrids, or just have better efficiency in mild hybrids.
And so how much smaller can you make an automobile battery if you don't have to worry about that peak? I guess one of the things is that real crank. Your car doesn't. If your battery is not doing well, it won't crank over, right? Because that's the biggest demand, is getting the car to start, right? So if you get these things to work, if this becomes fully integrated into cars, how much less juice do you need out of the battery just for running sake?
You typically, so a typical sedan passenger vehicle today, if you take out the micro or mild hybrid aspect and just look at a basic car, it's got typically a 50 to 60 amp hour battery in it. We have, in my labs in San Diego, we've built hybrid lead acid ultracapacitor replacements, and we're finding that the amount of lead acid you need is about 30 to 40 amp hours. So you can shave off, if you're 50 to 60 without the ultracapacitor, you can shave off maybe 30%. And that's without the big trade-off in hybrid devices with ultracapacitors is whether or not you put in management electronics or not, or if you just let the natural ESRs of the relative components dictate the current delivery. Of course, if you add in electronics, the cost goes up and it becomes more difficult to penetrate. So I'm talking about basically just a straight parallel hookup. You could basically take about 30% of the lead acid out.
But that would be for a conventional car, or for a hybrid also? Well, I guess hybrids aren't really lead acid. But
well, they divide hybrids up into a big spectrum. So they start with micro and then go to mild, and it goes beyond that. So a micro hybrid is basically a vehicle that has start-stop, and then depending on where you draw the line, either micro 2 or mild hybrid, you add in regen capabilities, typically from the alternator, and then later from traction motors in the drivetrain. So I'm talking about a micro hybrid that just has start-stop, no regenerative capability.
And Galen, let me ask you a question about materials. I'm just as a total novice in this area, how much? I mean, we heard that earlier presentation about really making phenomenal progress in a very short period of time. How much of that is dependent upon just dealing with materials we know all right, or really is it finding whole brand new materials that we are totally that we have to really discover?
That's an excellent question. Now, the answer is that I really believe quite strongly that the battery hub and also JCAP are on the right track, in the sense that when we design materials, as the synthesis side, we can make pretty much. We have a lot of freedom what we can make, but the question is, are we making? Is it the right thing? And the question, it's not only what the composition, of course, and the structure. That's important, but it's not the issue. The issue is really the performance at the end, and what you get in your supercapacitors or whatever you're trying to make. And so I didn't talk about this, but I mean, built into what's that approach in terms of making materials, there has to be good data mining, which is and also modeling, which is described and which we're fortunate to have at UCSB, but particularly it's emphasized strongly at the hub and also at JCAP and other places. And also the thing that is very, in my own personal, even down to the academic synthesis or materials perspective, that it's absolutely essential to look at, take a systems approach to what you're doing in terms of the chemistry, but also in terms of the properties, which are, the properties are multiscalar, multidimensional as well, and so you're trying to integrate those at the same time.
Yeah, the genome analogy is interesting. I hadn't heard it before. It's intriguing, but we also have to remember that once we even, got a good sense of what the genes were in the genome, that didn't actually end up opening doors as rapidly as we thought. So it sort of gives one pause.
Yeah. Well, the genome, I think conceptually it's a good idea. I have some concern based on experience of the time scale that some people have put into that, like 3 years from concept to market. That's or 5 years even. That's pushing it from what I know, and my experience has been in industry and elsewhere. But yeah, times are changing, maybe.
Yeah. Well, yeah, June, yeah.
Sorry,
Please.
Galen, thanks. This is a very important question. In addition to discovery of new materials, another thing, my background is like Galen. I'm a pure material scientist. Nowadays I talk about batteries. But very important issue is not only the material, but how different materials work together. It's more like a system problem. That's where there's a huge gap between, like, for example, the battery field and the materials community that I try to bridge the gap on in the last few years. I can give you many, many examples on, we have one fantastic material, but there's no place to put in the system. Like in batteries, we have some pretty nice, for example, high voltage spinel cathode material that increase the voltage. But what is good if you don't have an electrolyte to go with it, right? So that's a big problem. I can give you another example. You go to the literature, many papers in Science Nature about some exceptionally high capacity, supercapacitor electrode material. So you ask the question, if they're so good, why Maxwell is not using it, right? So if you look at that, thing is, you look at this material, think about, what I'm going to use as a counter electrode, how I'm going to make a device of it. It doesn't add up. So that's the gap between the materials community and the technology that we really need to cross the boundary to make things work.
We have about 15 minutes, and I want to leave room for questions from the audience. So if people have questions from out there, please step up to a mic.
Morning. Terrific presentation. Thank you, guys. I'm Craig Shields. My website, 2greenenergy.com, is an attempt to identify good ideas and take them forward. And a lot of them have to do with the kinds of discussions that we have here this morning. I have two clients whose subject matter I'd like you to discuss, if you don't mind. One of them has to do with zinc-air batteries. And if this guy were here, he'd be saying, well, I've been here for a day and a half and I haven't nobody's mentioned zinc-air. How is that possible? So if somebody could speak to that. The other one is a breakthrough in synthetic fuels. In other words, taking point sources of CO2 and off-peak wind or off-peak anything and synthesizing high-octane gasoline or high-grade diesel. And I think if he were here, he would say, I don't care if there's 16 different products. All we want, we don't want methanol because of the energy density issue. We want one or two really good ones. So if you could speak to both of those things, zinc air and synthetic fuels, thank you.
Who wants to take on zinc air?
Okay, so I can take a shot at the zinc air. Zinc air belongs to the class of metal air battery. It's actually one of the older technology among the metal air batteries. It's a primary battery, that not a rechargeable battery. It already demonstrated that it can be a useful product. But if you're talking about rechargeable battery, there's still a significant challenge. So few companies who want to make it work. One of them just bankrupt, I think. But it just take long time to make it work.
And Galen, you had one of your slides showed the incredible energy density of gasoline and diesel and so on. Why not go that route? Why fuss with all these electrochemical solutions and so on?
Yeah, well, part of the reason was indicated that the energy cost of doing that is not easy, and even converting from methane, for example, to these higher jet fuels and other components, we're still essentially industrial, we're still doing the Fischer-Tropsch syngas process, and that's a very high capital cost, high pressure, high temperature process, and so the idea of being able to, you can't put it on a fracking platform in North Dakota, for example, and so that's a big problem. But the whole idea, and the answer to partly responding to the question, has to do with I think the load leveling part. I understood there was some start on that in the Pacific Northwest with respect to using the wind as the renewable energy, and one of the electric companies there, maybe
Bonneville Power. Yeah.
And they were actually doing the load leveling by going actually to the homes or to the individual units to try to do that. And I think that's personally, I think that's a great idea. I'm not I haven't looked at the economics of it. I don't know about the economics of it totally, but at least it's taken that first step. Sounds to me like a very good idea. And I agree with you also. It was not usually like when we make chemicals, we're not interested. We want to make jet fuel. That's a mixture of many components. Fine, we're not trying to. We can focus the synthesis or the process to do that. Or we may want to make a petrochemical, for example. Again, referring to natural gas, you have propane, methane, ethane, and so on. Propane can be converted to propylene, which is a high commodity, high price, high value commodity material. So you go where it depends on what your customer wants to do and what he wants to make as to how you approach it synthetically or in terms of the product. It's like making a device. You have a figure of merit based on the cost and the cost value of what you're doing at the end. And so I think there's the issue is primarily the cost of implementing and putting things together and making it happen.
All right. Over here is the next question.
I wondered if you could compare the efficiency of the different technologies in terms of the energy out versus the energy to charge it. Obviously ultracapacitors are very high, but I was curious what the actual numbers were and how lithium or magnesium in particular, or the flow-in electrodes compared to each other.
So the lithium-ion battery, those kind of things, the efficiency can be very high, more than 99%. But the redox flow batteries, those kind of things, they are probably a range of 80%. That's what we call round-trip efficiency. So if you go talk with utility company, some of the challenges with chemical storage, right? The efficiency can be even lower, and then they begin to pull the plug. Right? So you have to be higher than 80%.
And Jeremy, do you want to?
Yeah, the ultracapacitor efficiencies, as you said, are very high. We have leakage currents that are measured in the very low number of milliamps compared to inrush and outgoing currents that are in the thousands of amps. And so we're 99% plus efficient.
On the other end of it, John, with respect to the chemistry, I showed one that was 7%. That's good actually for a leaf.
You're including the conversion.
That's the quantum efficiency.
Right.
Quantum efficiency from the photon averaged over the solar spectrum to the hydrogen produced.
So that's different from the round trip efficiency he's talking about. Yeah.
Would you mind if I make some comments?
No, help yourself, please.
Mind if I take
First, in answer to George Crabtree's question, when he asked, there is actually a need that the utility people say when I talk to them, they would like modular batteries, 50 to 100 kilowatt modules at the end of the distribution line. You can get a 1 or 2% gain in efficiency of the distribution to just do minor load leveling at the ends of the distribution line. They would like it standard size so they can move 1 module, 2 modules, 3 modules into that. The only downside and the technology need is it has to work at robust temperature ranges. If you can put it inside a building, it's a whole different ballgame. But if they have to be in a utility box outside, it's different. But they will die for that, even at $200 a kilowatt hour. They would love to have that. That would be game-changing, where it's right now about 400 or 500 of that cost. In terms of the comment about the ultracapacitor and the decision about whether you use the ultracapacitor directly to feed in, or do you actually have an electrical control circuit. Tesla, you probably know, has done a very good integration of the system. The generator motor is part of the electrical control system that gives the inertia. And over the last 3 or 4 years, they've made a very compact system, so they use the motor generator to be part of the smoothing and part of the conversion. And so, and the downside of ultracapacitors so far is cost and volume, but there are, I'm sure you guys are doing it, but I know a number of other companies looking at big breakthroughs in that, where then you can really, actually, Elon Musk believes now that maybe you can just dump the whole battery and get a really good ultracapacitor, but it's still that hurdle on that. Going back to the distribution, this is a model I've been trying to push for the last year and getting some traction, is that if the utility companies have a new model for how they supply energy, and this is not a new model, it's a reinvention of an old model by Edison and Westinghouse. The reason they wanted to develop a power distribution circuit is so people could use their light bulbs. And so they were mostly trying to get the electricity to people so they can sell them stuff. A new utility model and a growth model for them is they supply electricity, but they use the customers, whether it's a warehouse or a rooftop, as a place to put their generator and storage, again, locally. And then a lot of distribution issues and a lot of load leveling issues kind of go away, especially even in the $200 per kilowatt hour range. So that's something that if they can get the regulators and they can see on board, then their resistance to solar power will go away, because then they're on the profit side of it. So that's another comment. Zinc air and lithium air. It's true. For those who don't know, zinc air is the highest energy density of commercial batteries. It's the ones we use in hearing aids. There are a number of companies looking at rechargeable zinc air. There's 2 that I can't, because that's more confidential information, but there is being good progress made in the zinc air and in the lithium air space. With any new technology, one expects 90% of those companies to fail, but it's just the way it is. 90% of automobile companies, 90% of airplane manufacturers, you know, in the turn of the last century, in the 1920s. But it is looking, even though ostensibly at the very beginning you think, how can this be? Because the change in just the sheer geometry is so great when these air batteries charge up, that how could you ever make it rechargeable? And so you can have many, many, many cycles. But there's some cool stuff going on. Again, I can't tell I can't tell, you know, there's confidentiality issues, but so I can't do, but to your question of, you know, there's hope, but again, in the Department of Energy, we used to have an expression that goes back to Thomas Alva Edison. It goes something like this: there are liars, there are damn liars, and there are battery entrepreneurs.
And then there's the fuel cell guy.
but despite that, some of these things we believe will work. Okay.
Thank you.
Secretary, can I ask you a question?
Sure.
Because you talk about...
I'm ex-secretary, please.
So you just mentioned about the distributed generation storage. Those things are really are important. We know in the last few years in the budget request, there's something called the Grid Hub that supposed to address some of those issues. Can you make some comment on that? And what do you
I don't understand the question exactly.
The Grid Hub that's in the request for the budget.
Oh, the hub, the Grid Hub.
Yeah,
Yes.
so make some comment on that.
The hubs were always an uphill battle, despite the success of the bioenergy hubs, which, it was kind of the, Bodman, the precursor. I convinced Bodman, got to do this, and that's been very successful. The hubs that I started, I can't yet claim successful. The nuclear hub, which is the first one, is doing this, but I'm very hopeful on most of the other hubs. But every time you add a new hub, both the OMB and Congress gets very nervous and say you're making an obligation, and for 5 or 10 years into the future. We're probably not going to continue a few hubs just to keep the others honest. Okay? Getting the first 5-year tranche doesn't guarantee you 10 years, so you need to trim a little bit. And so the issue with the grid is very much more complicated, and it goes back to, I think it's David who said, it's perhaps the NREL study is perhaps an academic exercise, but it's well worth doing. I agree with that. It's academic in the following sense. It's very difficult to get all the players in the transmission distribution system, all the stakeholders, the distribution companies, all, the regulators, everybody to play. Most players have their own little turf, their own little sandbox, and they're very possessive about it, and they don't want anyone to even know what they're doing. And even in this, like the San Diego blackout, they had to call each other up to find out what they're doing because they don't trust having an automated system to tell them what they're doing. Okay, this is, phone call, what's happening in your area. It's just like 50 miles away. So to get them to actually play to get a national transmission distribution system is something that will take a decade, but there's so much to be gained from that. But there's not any national pressure to do it yet. There's no voter pressure to do it. There's no, and so they guard their own little sandbox, and that's their business model. I can control what I do, and I can't worry about, and for gosh sakes, I certainly don't want to do energy trading, at least in the western half of the United States. So these are cultural things that will have to change. Europe is getting better at trading electricity between countries than we are between districts within a state.
Very interesting, and obviously, thank you. Yeah, interesting implications for the battery conversation. I think we have time for one last question.
Thank you. My question's on battery weight. I thought lithium was really good for batteries because it's the lightest metal. So if we want to go to multivalent metals for the electrodes, but we're increasing the weight, how does that affect the weight of the final battery?
David, you want to take that?
Yeah, so first, I think in most of the applications, weight is actually not the critical metric. So if you look at most of these applications, it's mostly about either cost per kilowatt hour or for grid applications, or for most of the other applications, they're actually driven by energy density per unit volume, not by per unit kilogram. And even in a vehicle, people are increasingly focused more on the volumetric piece than on the weight piece, and that's because the volume controls how much car structure I have to drag around behind me, and that drives the weight of the vehicle more than the battery itself. I think one last comment is if you look at the weight of a battery, most of the weight of the battery is not the lithium ions in the battery. Most of the weight of the battery is the other stuff that has to carry along with it. Right? So even on a weight perspective, magnesium and these other chemistries wind up on a per kilogram basis being significantly ahead of lithium ion, though not as not as big a difference as it is on a per volume.
Thank you.
David, are we done?
Why don't we do one more?
One more, okay, good.
We are running a little over, but let's do one more question.
All right,
Okay.
thank you very much. Quick
Quickly.
question. We didn't hear a lot about safeties, and as I understand, Boeing and the FAA did not really find the root causes for the exothermic reactions, and as power density increases, so does the potential for exothermic reaction. So maybe you could share some insights on how you incorporate safety in your overall research and development, or the safety issues.
David or June, David, you want to take a step?
So we begin with the basic thermochemistry. So looking at the exothermic reactions and differential scanning calorimetry of the battery to understand what drives the temperature release. I think as George mentioned, there's a significant difference in the temperature where you go into thermal runaway. So the issue with lithium-ion batteries is the thermal runaway problem, which is at 120 degrees or something, they begin an exothermic release, which takes it hotter, right? So that's the thermal runaway problem. And from a design perspective, you want to think of the amount of margin you have between the highest operating temperature that the battery has and what's the temperature where things go horribly wrong. And I think when we look at chemistries, we assess the chemistries against that margin. So what is my minimum temperature at which I initiate a thermal runaway, and how does that compare to the maximum operating temperature of the battery? And the chemistries that we're looking at are typically, we screen them against that, and typically the chemistries we're looking at are vastly better than lithium-ion against that metric. So I think that's important for a couple of reasons. It's important because I think safety is going to drive the perception in the public environment of a lot of these technologies, and I think particularly if a plane goes down because of a lithium-ion fire, you will see a radically changed attitude to lithium-ion batteries on planes. And I think the other thing is that the cost of avoiding having such a catastrophic event is also very high. So when I talk to the automotive manufacturers, they say, give me your battery today, fully functioning, and I will test it for the next 5 years, and I'll put it in a commercial vehicle way out in the future. The cost of that means that lithium-ion technologies in a vehicle typically trail leading edge technologies by many years. And again, so in terms of cost of adoption as well as perception of the marketplace, I think safety is a very, very critical issue.
All right. Well, thank you all very much.
Let's thank our panelists.